Now let's develop a formal way for solving for the single period inventory problem by using marginal analysis. So if you remember from our last video, we looked at this profitability curve where again the horizontal axis is the Q and the vertical axis is the profitability. And we said there were two regions. Regions here to the left is when I ordered too little, and that means I might be short some products. And to the right is where I ordered too much, and there's a higher probability I'll have excess. And so what we want to do is figure out how can I find that Q star. So for single period problems, we have two costs. We have this excess cost, and this happens when the demand is less than what I wanted, than Q, right? And so this means I have too much product. And so for this, it's going to be when I have too much laying around, I have excess. Then I've also got the shortage cost when the demand is greater than Q for whatever I pick, and that's having too little product, right? I'm not going to have enough there. So what do I want to do? Well, I've got a continuous distribution of demand. So I'm going to be able to find what is the expected excess cost for the Qth unit. This is the marginal cost. That next unit is going to be ordered. Well, what is that going to be? It's going to be equal to that cost of being excess, and we already figured out what that's going to be. It's the cost of having an extra one times the probability that my demand is less than or equal to Q. So that's the expected excess cost for that Qth order. And I can do the same thing for the shortage cost of the Qth order. That's Q sub S times 1 minus that probability. And so what I have here are the two costs, the marginal cost for having too little and having too much. And you know, if my excess cost is less than my shortage cost, then I'm just going to increase my Q. How much am I going to increase my Q? Well, I'm going to increase it until they're equal, because essentially I'm going to climb this hill, right? Climb it up until the slope is 0. Think back to calculus, right? And so where the marginal costs are the same, right? That's where my maximum is going to be. So let's look at this in terms of the marginal cost. So what I have here is a chart. Again, the horizontal axis is the Q, and this is the marginal cost per jersey. That's the vertical axis. And so if I look at this blue line, which is the excess cost, this is the marginal increase, or the marginal cost for being excess. So if I only order 10, and remember my distribution here was distributed normally with a demand of 32 with a standard deviation of 11, and we're in units of thousands, right? 32,000 units with a standard deviation of 11,000. If I ordered 10,000 units here, then the probability that I'm going to have excess is pretty low. That means there would have to be, 9,999 units demanded or less, right? So it would be pretty low. As I get up and order a higher amount, if I order 60,000 units, the probability of me getting excess, of having excess jerseys lying around, gets pretty high. And so the marginal cost increases. And you see how it changes, and it's not linear. And that's a reflection of the underlying normal distribution. I can also plot in red the shortage costs. And again, we can look if I ordered only 10,000 jerseys when my expected amount is 32,000. Then I'm going to have a pretty high marginal cost because I expect it to be very short. I'm going to be short a bunch if I expect on average 32,000 and I only ordered 10,000. But at the other extreme, if I order 60,000, then chances are I'm not going to be short anymore, right? And so you see that these two marginal costs work in opposite directions. And when are they equal? Well, that's our optimal Q. Because when they're equal to each other, then that means I'm at the maximum of that profit curve. And so that tells me my Q star. So let's see this formally. So we already developed this equation. This is the marginal cost for excess, and this is the marginal cost for being short. We're going to set them equal to each other, and I'm just going to let you look at the algebra, but we're going to clean it up a little bit and turn it into this relationship where the probability of the demand being less than or equal to Q, my order quantity, is going to be equal to this relationship of C sub S, the shortage cost, over the sum of the excess cost and the shortage cost. Hopefully this looks really familiar to you. It's the same critical ratio we saw in the EOQ problem with planned back orders. It's just a ratio of shortage over the total of the excess and shortage costs. So let's see if we can talk about that just a little bit more. Think of it like a seesaw. And on one end, I've got my cost of being excess. And at my other end, sitting at the other end of the seesaw, is the cost of being short. And so the question is, where do I put the fulcrum to make it balanced? We can think of this distance, right, from the fulcrum to CE as being equal to the critical ratio, which is C sub S over C sub E plus C sub S. Just this term, right? So if one case, what if CE equals CS? Where will the fulcrum be? Right in the middle. Right in the middle, because you have half and half. But what happens if, say, CS is equal to twice as much as CE? So my shortage cost is twice as much as if I have excess cost. Well, what's my critical ratio going to be? I can just plug this in, right? CS is, so it's 2 CE over 3 CE. It's going to mean that the critical ratio is 2/3, right? So what's going to happen to that fulcrum? It's going to move 2/3 of the way there, right? So my fulcrum here, because what happened? This got twice as heavy. This became the big guy sitting in, there's a little guy half the size over here. So as my critical ratio gets bigger, as my CS gets bigger, my cost of being short, my critical ratio gets bigger and it moves closer to that. So just like a seesaw, you could look at the other way. If CE got really big in proportion to CS, then the fulcrum would move the other way. So you can think of it as just a balance. Where is the balance between the two? Now if I look at the left side of this equation, the probability that X is less than or equal to Q, we should be able to remember what that is, thinking back to our beloved normal curve. And that's my best estimation of a normal curve. And I've got some mean demand here. Then what I'm saying is this probability that X is less than or equal to Q is simply this area under the curve where this is Q. And so this is that. So what happens as the critical ratio, right here I said this is the example where the cost of shortage is equal to twice the cost of excess. So the critical ratio is 2/3. As this critical ratio gets bigger, what happens? This Q is going to have to get bigger because I have to cover, let's see, this amount, right? I would have to make that amount of the probability over there is equal to 2/3. So the lesson here is as the critical ratio gets bigger, which means the cost of shortage is increasing, then I've got to cover more of my demand distribution. That's all that it means. We're looking at normal curve now, but we'll look at other distributions later. All it means is I need to cover that percentage or that probability of that demand happening to be optimal. So now let's apply this analysis to the NFL jersey problem.